In this lesson, we're going to talk about the properties of variance. So variance does not depend on the actual values that a random variable takes, or even the average value of a random variable. It only depends on how spread out the values are of the random variable. So let's consider an example with three different random variables, x, y, and z, where the probability that x equals 1 is 1/2, and the probability that x equals -1 is 1/2. The probability that y is 10 is 1/2, and the probability that y is -10 is 1/2. And the probability that z is 9 is 1/2, and the probability that z is 11 is 1/2. So notice that the distance between the two values of x, 1 and -1, is 2, and the distance between the two values of z, 9 and 11, is also 2. So they're just as spread out, even though z is a lot larger than x, or larger anyway. And the values of y are much more spread out, so they're either 10 or -10. So we're going to use the formula for variance, e of x squared minus the quantity of e of x squared, to find the variance of each of the random variables. So we'll do this by first computing the expected value of each random variable, and by x here I mean a general random variable x, not necessarily the x that's 1/2 chance of being 1 and 1/2 -1. So we'll find the expected value of all the random variables. Then we'll find the expected value of the random variable squared, and then we'll use this formula to compute the variance. Alright, so the expected value of x is 1 times 1/2 plus -1 times 1/2, which is 0. The expected value of y is 10 times 1/2 plus -10 times 1/2, which is also 0. So x and y have the same expected value, but z has expected value 9 times 1/2 plus 11 times 1/2, which is 10. So x and y are both centered around 0, while z is centered around 10. And to compute the expected value of the squares, we square the values that the random variables could be. So the expected value of x squared is 1 squared times 1/2 plus -1 squared times 1/2, which equals 1. And the expected value of y squared is 10 squared times 1/2 plus -10 squared times 1/2, which is 100. And the expected value of z squared is 9 squared times 1/2 plus 11 squared times 1/2, which is 101. Now we can take each of these values, so the expected value of x is 0, and the expected value of x squared is 1, so we take 1 minus 0 squared, which is e of x squared, and get the variance of x is 1. Then the expected value of y is 0, and the expected value of y squared is 100. So we get 100 minus 0 squared, which is 100. And doing the same thing for z with 10 and 101, we get the variance of z is 101 minus 10 squared, which equals 1. So notice that the two variables that were equally spread out, x and z, which took two values that were a distance 2 apart, both have the same variance. Their variance is 1. And y, which was much more spread out, has a lot higher variance. It has variance 100. And it didn't matter that x and y were centered around the same value. If we take the square root of the variances, we get the standard deviations. So both x and y have standard deviation 1. And x and y both always deviate by 1 from the mean. So the mean is 0 for x, and it's always either 1 above or 1 below 0. And the mean for z is 10, and z is always 1 below or 1 above 10. Standard deviation doesn't always work out so nicely, but because these are really simple examples, it's working out exactly. Same thing goes for y. If we take the square root of the variance, which is 100, we get a standard deviation of 10. So the standard deviation of y here is 10, and it's always 10 away from its mean, either 10 above or 10 below its mean. So since variance doesn't depend on what the actual values of the random variable are, only how spread out they are, adding a constant to a random variable doesn't change the variance. So if we were to draw, for example, x on a number line, and it takes the values -1 and 1, and then we look at x plus 1, now x takes on the values 0 or 2, but the values x takes on are just as spread out as they were before, so it doesn't change the variance. And you can use linearity of expected value to show that the variance doesn't change. So using the formula we've been using, the variance of x plus c is the expected value of x plus c squared minus the expected value of x plus c quantity squared. To solve this, we will first square this value, so we get x squared plus 2cx plus c squared, and we will use linearity with this expectation since the square is on the outside. So this is e of x plus c quantity squared. Then we reverse those steps. So now we can use linearity here. So e of x squared plus 2cx plus c squared is e of x squared plus 2c e of x plus c squared. And then on this side we can square now. So we have e of x plus c quantity squared, which is e of x squared plus 2c e of x plus c squared. Then there's this minus here in front of this whole quantity. So these are all negatives, and that means that this plus c squared and this minus c squared cancel. We have a plus 2c e of x and a minus 2c e of x that cancels. And that leaves us with e of x squared minus e of x quantity squared, or the variance of x, which means that these two things are equal. However, if we multiply a random variable by a constant, that does spread out the values. So if we have an x, which is taking the values -1 or 1, and then we multiply by 2, so we get 2x. Now the values of x are -2 or 2, and they're more spread out than they were before. And it turns out that if you multiply by a constant c, it changes the variance by c squared. So the variance of c times x equals c squared times the variance of x. And once again, you can use linearity of expected value to show that this is true. So the variance of cx is the expected value of cx squared minus the expected value of cx quantity squared. And once again, we square the inside first, so it's c squared x squared on the left, and we use linearity first on the right. So e of cx is ce of x. Then we use linearity on the left, so pull the c squared out, c squared e of x squared, and square left or the right hand side. So ce of x squared is c squared e of x squared. Now the c squared is a coefficient of both terms, so it can be pulled out. So it's c squared times e of x squared minus the quantity e of x squared. Oops, and this square should be on the outside. That's a typo. Because it's on the outside here. And e of x squared minus the quantity e of x squared is the variance of x. So these two things, once again, are equal. Variance of cx is c squared variance of x. And a corollary to that, which just combines the two facts that we just showed, was that if a and b are constants, then for any random variable x, the variance of ax plus b, so if we do a linear transformation, the b doesn't matter, it's a constant, and the a comes out and is squared, so it's a squared times the variance of x. And the last fact in this lesson is that if x and y are independent random variables, then the variance of x plus y is equal to the variance of x plus the variance of y. So let's verify that, once again, using the formula, that the variance of x plus y is e of x plus y squared minus e of x plus y quantity squared. Same strategy as before. We're going to actually do this a little bit slower, the way that I broke this down. So we're going to only use the linearity of expected value on the right term here. So it's e of x plus y squared is e of x plus e of y quantity squared. Then I square both terms. So the x plus y squared is x squared plus 2xy plus y squared, and e of x plus e of y quantity squared is e of x squared plus 2 of e of x e of y plus e of y squared. Oh, darn. And I have another typo here, so this should have an e. So let's see. This should be e of x times e of y. And here we use linearity of this expected value. So e of x squared plus 2xy plus y squared is e of x squared plus 2 e of xy plus e of y squared. And this is where we're going to use the independence. So my independence of x and y, e of xy is e of x times e of y. So this e of 2 e of xy minus 2 e of x e of y cancel. That is, this term and this term can cancel because of independence. And if we cancel those two terms, we're left with an e of x squared plus an e of y squared minus an e of x quantity squared minus an e of y quantity squared. So that's just pulling the terms that didn't cancel from up here. That gives us this. And then just rewriting, this is e of x squared minus e of x quantity squared plus e of y squared minus e of y quantity squared. Just written here, which makes it easier to see that this part is the variance of x, and this part is the variance of y. So when they're independent, the variance x linearly, the variance of x plus y is the variance of x plus the variance of y. I am going to go correct those two typos, so hopefully whenever you read this lesson for the first time, the typos won't actually be on the blackboards.